A gene string can be represented by an 8-character long string, with choices from A, C, G, and T. Suppose we need to investigate a mutation from a gene string startGene to a gene string endGene where one mutation is defined as one single character changed in the gene string. For example, AACCGGTT greater than AACCGGTA is one mutation. Here is the code of minimum genetic mutation. This code implements the graph theory concept to solve the problem of finding the minimum number of mutations required to convert the startGene string into the endGene string. Each gene string is considered as a node in the graph, and each mutation is considered as an edge between two nodes. The code uses a breadth-first search algorithm to traverse the graph and find the shortest path from startGene to endGene. The queue data structure is used to keep track of the gene strings to be processed next, and the scene set is used to keep track of the already visited gene strings to avoid visiting the same node multiple times. The code also checks if a mutation is valid or not by checking if it is present in the gene bank, which is stored in the bank set. The variable num of mutation is used to keep track of the number of mutations that have been applied so far. The problem is to find the minimum number of single character changes, mutations, required to convert the startGene string into the endGene string, given a gene bank that contains all the valid gene mutations. In other words, you have to find the shortest path from startGene to endGene, where each step in the path represents a single character change. If there is no such path that reaches endGene, then the result should be -1. To solve this problem, you may use graph theory concepts, where each gene string is a node in the graph, and each single character change is an edge between two nodes. The goal is to find the shortest path from startGene to endGene, while considering only the gene strings that are present in the gene bank. The code first initializes some variables and data structures that will be used later. The scene set is used to keep track of the already visited gene strings, and the bank set is used to store the gene bank for faster lookup. The queue data structure is used to keep track of the gene strings that need to be processed next. The choices array contains the 4 characters that can be used to make a mutation, A, C, G, and T. The variable num of mutation is used to keep track of the number of mutations applied so far. If the startGene string is the same as the endGene string, then no mutations are required, and the function returns 0. The startGene string is added to the queue and marked as visited in the scene set. The code enters a while loop, which continues until the queue is empty. In each iteration of the loop, the code processes all the gene strings in the queue. The code takes out the first element from the queue, which is the current gene string to be processed. If the current gene string is the same as the endGene string, the code returns the number of mutations applied so far, num of mutation. For each position in the current gene string, the code tries changing the character to each of the 4 choices, A, C, G, and T. The code checks if the mutated string is in the gene bank and not already visited, and if so, it adds it to the queue and marks it as visited in the scene set. If the queue is empty, and the endGene string has not been found, the code returns -1, indicating that there is no way to convert the startGene string into the endGene string using the given gene bank.